Let's now talk about lithium-based organometallic compounds and several different chemical reactions that they undergo. Organolithium reagents have the generalized formula of R bound to lithium, where that bond is a covalent bond. However, just like Grignard reagents, we actually write them up as if the alkyl group, the R group, is nucleophilic. So I have a lone pair of electrons with a negative charge, and I have lithium here as a positive charge. So organolithium reagents can be produced from alkyl halides, vinyl halides, or aryl halides, just like Grignard reagents. So I start with a halide compound where the halogen can either be chlorine, bromine, or iodine. Most often it is still bromine. I react that with lithium metal, 2 equivalents. I form the organolithium compound, and I also form this lithium halogen salt. 2 examples of lithium reagents are I take N-butyl bromide, react it with 2 equivalents of lithium. I form N-butyl lithium and my lithium bromide. I can also take an aromatic halogen, react that with 2 equivalents of lithium, and I get phenyl lithium, and I get lithium bromide. Notice in this case, I have hexane here as one solvent, and I have ether as one solvent. It turns out the lithium compounds are a little more forgiving on what type of compound you can use. It still has to be very dry, but I don't need the oxygens to stabilize the lithium compound here, my organolithium compound. Let's now do a practice exercise where we show how you can synthesize the following 4 alcohols from compounds that contain no more than 5 carbons each. And let's do all these syntheses using organolithium compounds. You will see a lot of similarities to Grignard reagents. So here, I look at these molecules and I find my oxygen and find that carbon. That carbon in one of my starting materials must have been a carbonyl group. So let's go ahead and break that molecule up sort of in a retrosynthesis. This half of the molecule had to have been a 5-carbon alkyl halide. This half of the molecule had to have been a 3-carbon carbonyl. So if I start with this alkyl halide, I react it with 2 equivalents of lithium. I form the organolithium compound. I add to that a 3-carbon carbonyl group, in this case would be acetone. Work that up with acid. I form the tertiary alcohol shown here. In the second example, I look for the carbon attached to oxygen. I split that molecule up so 1/2 would have been a carbonyl group in my original reactants, and the other half would have been an alkyl halide. So I'm just going to add a bromine here. So I start with this reagent. I react it with 2 equivalents of lithium to form the organolithium compound. I then throw in my 1-carbon carbonyl group, which would have been formaldehyde. React with that carbonyl, work it up with water to form my primary alcohol. In this case, much like we did for the Grignard reaction, I'm going to split this up twice here. So here's 5 carbons, here's 5 carbons. Both of those had to have been alkyl halides. Here's a carbonyl. Here's a carbonyl in my original molecule. That would have been oxaldehyde. So I start with 2 equivalents of the alkyl halide, react it with lithium, in this case excess lithium. I react it with oxaldehyde, work it up with water. In this fourth example, I'm going to do this retrosynthesis similarly. I'm going to look for the carbon attached to oxygen. When I split that up, that carbon had to have been bound to a carbonyl group, so double bond oxygen. In this case, I need to form an alkyl halide that's going to be vanillic, so my halogen is attached directly to a double bond carbon, and I can do that with lithium. React that with lithium, I form the organolithium compound, I react it with formaldehyde, work it up with water, I create that compound. This cannot be done with the Grignard reagent. I cannot make a Grignard reagent with this vanillic alkyl halide. So I have to use lithium in this case. Lithium compounds can actually undergo a chemical reaction called transmetallization, where I actually have metal exchange. So I first form my organolithium compound. I then throw in another metal. In this case, I'm going to throw in copper iodide. And actually, my copper exchanges with my lithium to form an organocuprate molecule. And I form lithium iodide. This happens because I want to create a less polar molecule. So if I look at electronegativities, carbon has an electronegativity of 2.5, lithium 1.4. The difference is 1.1. If I do a transmetallization, a metal exchange with copper, my carbon still has an electronegativity of 2.5. My copper has an electronegativity of 1.8, which is only a 0.7 electronegativity difference. So this is a favored reaction. It turns out there are a lot of interesting reactions that organocuprates undergo. So my covalent bond is between copper here and two different methyl groups. Noticing that I start off with two equivalents of the organolithium compound, and I created one equivalent of my organocuprate compound. These organocuprate compounds are often called Gilman reagent. Gilman actually discovered that you could use these organocuprate compounds to actually do coupling reactions. So let's look at a few examples. I start out with an organolithium compound. I react that with copper iodide in the presence of tetrahydrofuran, which is a cyclic ether. I form the organocuprate. If I take that organocuprate and I react it with an alkyl halide, I actually do a coupling reaction. It's like an SN2 reaction, where this group here actually reacts as if it is a nucleophile displacing that bromine atom. I've actually coupled two alkyl groups together. Let's compare the reactivity of a Gilman reagent to my Grignard or my organolithium compound. Recall that the most common reaction for Grignard and organolithiums are to react with carbonyl groups to form alcohols. So here I start with cyclohexanone, react it with methyl magnesium chloride, a Grignard reagent, work it up with water to form this 1-methyl cyclohexanol. Gilman reagents do not react with carbonyls. So if I took that cyclohexanone, I put in my dimethyl copper lithium Gilman reagent, I actually have no reaction that occurs. This is interesting in the fact now that I can have two different reagents, one that does react with a carbonyl group, one that doesn't. So if I have multiple functional groups on a molecule, I can actually selectively react in one area of a molecule over another area. Let's look at where Gilman reagents are actually used extensively. That is actually for doing coupling between vanillic or arylic halides. So here I have a vanillic halide where my halogen is attached directly to an sp2 carbon. When I react that with my Gilman reagent, a cuprate that contains two ethyl groups here, I replace that bromine with my ethyl group here. I can also do that same Gilman reaction with aryl halides. Again, my halogen is attached directly to an sp2 carbon. I have a ethylene group here that will replace now my iodine, so I've made a vanillic aromatic compound here. When we do this type of chemistry, it turns out that in the reaction, the configuration of the double bond is retained. So let's look here. I have a cis alkene here, where my halogen is on the same side as my R group attached to my double bond. I react that with my Gilman reagent, which has a methyl group attached to it. My methyl group ends up being where my halogen was, on the same side of the double bond. That's true for both cis, and that's true for trans. Very useful chemical reactions. Gilman reagents do react with epoxides, however. In this case, we're looking at ethylene oxide. If I place that in the same reaction vessel as this diethyl cuprate compound, my Gilman reagent, I actually are adding 2 carbons onto my epoxide here. So I create a 4-carbon system. 1 2 carbons plus 1 2 carbons, and I have to react that up with a little bit of acid to protonate my oxygen. What kind of R groups can I have on a Gilman reagent? I can either have a primary alkyl, I could have a methyl, a aryl, or I could have vanillic or allylic. So these aryl and vanillic are the real utility of using a Gilman reagent, because I cannot do that with a Grignard or an organolithium compound.